Today we're gonna derive an expression for a steady state absorption flux of a gas A into a liquid beam of thickness theta, beyond which the concentration is approximately zero. So I'm gonna draw a diagram in here. So this is our film. Let's draw this. It's the thickness of theta, and then here's z equal to zero. And so this part is gonna be liquid. And out here is going to be gas, vapor, and this is going to be the interface. So today, going to talk about the absorption flux. We're going to find flux of Na at Z is equal to zero. Um, so first we know that gas goes through liquid from a higher concentration or diffuses. It diffuses from high to low concentration. So we're going to use Fick's law because this is not moving by convection. So we're going to have flux Fick's law Na is equal to negative d d derivative of concentration of A over dz, and then the negative sign. And so you know that during the process, the rate of reaction, there's a reaction happening, first order reaction with reaction K. So we can derive equation for our reaction. So we can have negative R, reaction of A is equal to KCA. All right. The reason why there's a negative is because A is being consumed. So therefore we have the balance equation. D dCA over dZ minus KCA is equal to zero. And so that's our balance equation. I'm sorry guys, so I made a mistake over here. So when we do the balance equation, this is supposed to be, the flux is supposed to be in second derivative. And so we can have d c square A d square CA over dz square. And then so now we're gonna define variable m to simplify d and k. So we're gonna have m is equal to square root k over d. So when we rewrite, substitute this into our equation, we have dCA over dz square minus CA minus m square CA equal to zero. So now at this part, we're gonna solve it with using second order homogeneous linear linear um differential equation. So now moving on to our general solution is CA at distance Z is equal to A cosine of M theta plus B sine hyperbolic sine of M, and that's equal to zero. And then now we have our boundary condition at Z is equal to zero. C concentration of A is concentration of AI. So hey guys, sorry I made a mistake over here. It's supposed to be cosine MZ instead of M theta. So when we substitute C is equal to zero, CA is zero, we would have A, we have an A because sine hyperbolic sine zero is zero. And then, so we know that A is equal to C concentration of initial concentration of I at the interface. So now we know that CA at theta is equal to theta is equal to A hyperbolic cosine of M theta plus B hyperbolic sine of M theta. So since we know A is CAI, we have B is equal to CAI is equal to CAI co hyperbolic cosine M theta over sine hyperbolic sine M theta. So our complete equation would be CA would be equal to CA cosine hyperbolic cosine M theta plus CA um hyperbolic cosine M theta over hyperbolic sine of M theta times um sine hyperbolic sine of MZ. Let me just double check my word. Oh, just one over here should be MZ. So that's the complete equation that we have, and then we're going to simplify it. So CA would be equal to hyperbolic cosine of MZ times hyperbolic sine of M theta minus hyperbolic cosine of M theta times hyperbolic sine of MZ over sine M theta hyperbolic. And then after some simplification, we have sine equal to hyperbolic sine of theta minus z over hyperbolic sine of m theta. It's theta over z. So that's the final equation I have for concentration of A um for a steady state absorption flux of a gas A into liquid feed. So yeah, that's how we solve for the second order homogeneous linear differential equation. Thank you so much for listening.